Hello students, welcome back again to my classroom advanced classes, chemistry class we are taking now, and this is the fourth class for us. We have done solid state, chemical and ionic equilibrium, the thermodynamics. Next, this is electrochemistry, and one more important topic and more conceptual topic. Okay, so again, like all we see through some applications here. Okay, go ahead. So what is the first one? The reaction, that is half H2 plus AgCl solid, is giving H plus aqueous, Cl minus aqueous and Ag solid. In which of the following galvanic cell this cell reaction exists? So mostly if you see the electrochemistry, the major applications of electrochemistry, we can do it or we can solve it only when we can able to predict the what is the cell reaction or how the cell in a galvanic cell, how we constructed the cell. So we could able to predict this thing, then this most of your questions will be or most of your applications are simply solved. So how we actually develop a galvanic cell? So the basic thing in a galvanic cell is we have two different half cells. Main part, basic part if you see. So there is two half cells. But what is a half cell? Where there is some potential difference. Then how to develop a potential difference? The potential difference is developed when we consider an electrode and there is some electrolyte solution. So between this solution and the electrode, we have the potential difference. So how the potential difference will generally develop? It's a simple thing. When there is an element in a two different oxidation state, it develops the potential difference. It exists in the solution, maybe it exists at the electrode and in the solution again. That means we just say suppose zinc in zinc sulfate solutions or zinc ions, then the potential difference develops. Copper sulfate solution, copper ions, potential difference develops. Maybe we have suppose a hydrogen electrode. This is a platinum electrode. On that platinum electrode we have hydrogen adsorbed. So we close this electrode with a compartment where we pass the hydrogen gas into it. So the hydrogen was adsorbed onto the platinum surface. So the hydrogen is existing on the platinum surface, on the electrode surface. Then there is H plus ions in the solution. They'll develop the potential difference. So how to construct a half cell? A half cell is constructed when there is an element in a two different oxidation states. It exists in the solution or it exists in the solution and on the metal surface. So zinc rod, zinc sulfate solution, copper rod, copper sulfate solution. Like already we are saying hydrogen gas is passed on to the platinum surface and H plus ion exists in the solution. We even see this type of half cells also. Means we say there is a platinum electrode which is just kept because in that electrode for any potential difference an electron is there. That electron can be moved from one end to the other end of the galvanic cell. So that we need to take a platinum surface, suppose electrode surface, and we have Fe plus 2 and Fe plus 3 in the solution. So element is there in a two different oxidation state in the solution. Then it develops the potential difference. Then what type of reactions happens in each half cell? That if you can able to do it, if you can predict it, then your all the electrochemistry applications, whether it is in a galvanic cell or electrolytic cells, we could able to simply solve it. So let us see what is this now. In which of this we have the cell reaction which is represented there. So what is the cell reaction here is given H2 is converted. So let us see in each, because with this we just try to see in each half cell what is this construction. This cell is nothing but Ag rod is kept, silver rod is kept in an AgCl which was dissolved in KCl solution. So a metal sparingly soluble salt in a common ion. What is this is? We have silver rod in a silver nitrate solution. So what is the cell reaction in this? So whenever it is galvanic cell representation is there, the first part is nothing but anode, the second part is nothing but a cathode. So what is this is anode, this is a cathode. So in this, what is anode reaction and cathode reaction is? Anode reaction is nothing but Ag, means we just suppose write only reduction reactions. So what is the cell reaction here? Reduction reaction at anode. Actually anode undergoes oxidation, but let us write as reduction AgCl plus electron giving Ag plus Cl minus. Reduction reaction means if it is, what is oxidation? Reverse reaction. So what I write, if it is an oxidation reaction, we just completely reverse this. That is Ag plus Cl minus is giving AgCl plus electron. So what is the cathode reaction at this now? It's a silver ion which is coming from silver nitrate. So Ag plus electron gives Ag. So if you just see the cell, let us say composition, how it is half cell is made. That half cell representation also can be seen in the cell reaction. What is you are seeing here is silver rod, AgCl solid, Cl minus. So we kept silver rod in an AgCl solution, means AgCl which was dissolved in a KCl solution or a Cl minus ion solution. Some Cl minus should come. So what is this is? Ag plus electron, Ag. So Ag rod is there in a silver ion. That's it, simple. So what is the cell reaction, overall cell reaction for the first one? It's nothing but Ag. This electron and electron gets cancelled. This silver and this silver actually cancels. So Ag plus Cl minus is giving AgCl. That's it. But this Ag plus is at the cathode. Cl minus is at anode. That's it. So it is not our up condition. What is the cell reaction in the B? So what is in the B? Platinum rod, hydrogen and HCl. Here silver nitrate. So what is in this? What is anode reaction is? It's an oxidation of hydrogen here. So it is a hydrogen half cell. So it is nothing but H2 is converting into 2H plus 2 electrons. If you want to write half, this is 1, this is 1, this is half. What is cathode reaction should be? It's again silver nitrate is there in a silver rod in a silver nitrate. So Ag plus electron giving Ag. So net reaction is this. So is it that? No. So what is the net reaction? Half H2 plus Ag plus electron cancels. So we have to add the two reactions to get the net cell reaction. For that you just say the electrons has to be balanced. So it is Ag plus H plus. So this is not also. So this is not our option, this is not our option. So let us see the other thing. H2 in case of HCl and AgCl is solid which was dissolved in HCl. So your HCl solution is common for anode and is common for cathode. That because we dissolved AgCl in HCl solution. So that H plus which is there in the solution is developing the potential difference at anode and the Cl minus which is affecting the potential difference at cathode. Because in case of a sparingly soluble salt, the potential difference will be affected by the common ion concentration. That is, the Cl minus ion concentration affects the potential difference at this. Similarly here, Cl minus which is coming from HCl affects it. So in the C option, what will be our cell reaction at anode? Anode cell reaction is now nothing but again only same. H2, that is half H2 is converting into H plus plus electron. What is cathode reaction is? It's a reduction reaction like what we already written here. AgCl in a Cl minus. So AgCl plus electron giving Ag plus Cl minus. So what is the cell reaction? Half H2 plus AgCl is giving H plus Ag plus Cl minus. Clear? So this is our cell reaction what we require. So this is our option. Even if you just see in the last case also, this is nothing but an aqueous solution that has in this case also an aqueous solution of KCl contains some H plus. So here also the same cell reaction exists because Cl minus is again common for anode compartment and as well as for cathode compartment. So HCl or KCl. In HCl directly you have H plus, but in an aqueous solution of KCl we also have H plus that is coming from water because it's a salt. So an aqueous solution of salt, anyhow aqueous condition, there is some H plus concentration. So this is also can be possible. So there are two possibilities. So the same cell reaction exists at anode and cathode in these two compartments. And your potassium is, as we just generally say, they are spectators always. Here, so both C and D, where the cell reaction is same. Now let us move to the next. Now there is an equation again, Cr2O72 minus H plus 2 electron giving 2 Cr3 plus and 7 H2O with a potential of 1.3. This is a standard potential. Then Cr2O72 minus acts as a better oxidizing agent in the solution when all other species are at unit concentration. Means all other species means the dichromate ion, this chromium plus 3 ion, whatever that exists other than the H plus, they are at same concentration, unit concentration, but maybe H plus concentration is changing. But what is the condition for a compound or a chemical species to behave like a better oxidizing agent? We say when its reduction potential is high, then the reduction ability is more. When its reduction ability is more, then we say it is a stronger oxidizing agent. So if oxidation has to means oxidizing agent, the reduction reaction has to take place so easily. So what is the condition here? The potential has to increase. So according to Nernst equation, what we say? E cell should be equal to E naught of the cell minus, let us say we write as 2.303 RT, otherwise at temperature 0.059 by number of electrons log at 25 degrees centigrade normal temperature condition. Reaction quotient. So what is reaction quotient here? It's nothing but actually for this reaction, what is reaction quotient for us? Q. It's nothing but Cr plus 3 concentration square by, because water concentration we take it as unity, pure liquids, then Cr2O72 minus concentration and H plus concentration whole to the power of 14. But he said chromate, dichromate concentration and chromium plus 3 concentrations are unity. So it is just becomes C1. So what is your reaction quotient effectively now? It's nothing but 1 by H plus concentration whole to the power of 14. So if the potential has to increase, this term should become plus. If this term has to become plus, the Q value should become low. So when Q value is low, when H plus concentration is low, if the H plus concentration is low, what happens is it comes to numerator and becomes plus. So don't see the H plus concentration. So what we say, if Q value has to be low, what is Q value when it is low? When this becomes high. So when the H plus concentration is high, the Q value becomes low, then the potential will increase. So as Q value decreases, E cell increases. In this case, or generally any case. So the Q is nothing but 1 by H plus. So H plus concentration has to be more. So in which case the H plus concentration is more. Okay, let us predict it. What is the first one? It's acetic acid and sodium acetate. So it's nothing but a buffer solution. But concentration of the acid and concentration of the salts are same. So what is pH? Is nothing but, clear? pKa. So pH in this case, first option, pH is equal to pKa. So even you can predict instead of H plus concentration, we can even predict the pH. If H plus concentration is high, what does it mean is your pH value should be low. Clear? So when the pH is low, it happens. So what is pH here? According to the given condition as 4.78. Let us see what is the next thing. There is 10 to the power of minus 6 mHCl. So what is H plus concentration in such cases? We have 10 to the power of minus 6. So that is the B option. It is H plus concentration. Generally we say HCl is a now strong air acid. So what is H plus concentration? 10 to the power of minus 6. That is coming from HCl directly. But when the H plus concentration is very low in a strong acids, then what we do? We even add the H plus concentration of water, and it is general approximation is it is also 10 to the power of minus. So what is this value maybe? It is 10 to the power of minus 7 if you take common. Then it is 1, this is 10. So it is 11. So 11 into 10 to the power of minus 7. So what is this maybe? This is around 2 into 10 to the power of, we will get 1.8 into 10 to the power of minus 5. That is as H plus concentration. Because when you take antilog of this 4.78, we get that around 1.8 into 10 to the power of minus 8. We generally know acetic acid, Ka value. So from that you just try to predict it. Clear? So it is now 10 to the power 11 into 10 to the power minus 7. So the Q value has to be low, H plus concentration has to be high. So H plus concentration should be high in this. So let us see. So this is one what we predicted, this is the other one what we predicted. What is in this case? In this case POH is equal to nothing but PKB now again. So what is OH minus concentration from here? What we can take now? As we are taking the H plus concentration as 1.8 into 10 to the power minus 5 here, we can take OH minus concentration here as 1.8 into 10 to the power of minus 5. So what is now H plus concentration? It's nothing but H plus concentration from here as 10 to the power of minus 14 by that. So it is H plus concentration is nothing but 10 to the power of minus 14 by 1.8 into 10 to the power of minus 5. So it comes around now 10 to the power of minus 9 into 1 by 1.8. So it is somewhere 10 to the power of minus 8. Or you can take 10, you can take 10 to the power of minus 10. So it is anyhow again low, or some value what we are getting for the C. So what is in this case? This is 10 to the power of minus 6. This is 10 to the power of minus 6 what we predicted. So for the D option, what we see is OH minus concentration is this much, that is 11 into 10 to the power of minus 7. Same way, what we have done for the stronger acid, we will do for the same for the stronger base. So what is H plus concentration from here? H plus concentration from here is 10 to the power of minus 14 by 11 into 10 to the power of minus 17, minus 7. Sorry. So it again comes as 10 to the power of minus 8 somewhere. So 10 by 11 into 10 to the power of minus 8. So which is having higher value? The first one only, that is 4 point. So first option where the H plus concentration is clear, high, there the potential will increase, there the ability of dichromate to behave as a stronger oxidizing agent. I think clear? So even though it may be a buffer type, even though it is a stronger acid, so the calculations are H plus concentration what we predict at this and at this says here the H plus concentration is more than this. So that condition you should follow carefully, because don't directly we can take it is a stronger acid, its H plus concentration is high. Maybe the concentration of the acids are so low, then it will change. Okay, so that type of applications is very important. Now coming to this, so predicting the potential here. So we have to predict the potential of this ClO3 minus is converting into directly suppose Cl minus. What is the potential? At the different conditions it is given. But generally we say potential is an intensive property. Actually we should not add the potentials. We should not subtract the potential. They are not additive. So what we do? Why sometimes we say what is the cell potential? It is cathode minus anode, reduction potential of cathode minus reduction potential of anode. But when we are doing that, when the cell electrons are, half cell electrons are same. So at anode and cathode, if the cell reactions are same, the net cell reaction or number of electrons in the cell, half cells are same. In the total cell also it will be the same. But when we have the different cell reactions here, that is what is the reaction actually what we require is ClO3 minus conversion into Cl minus total. So what are the different conditions that are given? Let us see. So here the total number of electrons involved, if you just even take, what is the oxidation state of chlorine here? +5. What is the oxidation state of chlorine here? It's +1. So what is n factor that involves in this process is, or total number of electron involves in this process is nothing but 4. It's a +5 to +1. So 4 electrons are gained here. So when you write the cell reaction at this stage, means half cell reaction assuming it, what is the cell reaction at this stage maybe? That is ClO3 minus is converting into ClO minus plus 4 electrons. So you have to balance the reaction now with respect to the charges, with respect to the acidic or basic condition, but your number of electrons in the half cell reaction will not be affected, because it depends only on the change in the oxidation states. So maybe if it is an acidic condition, how we balance a half cell reaction using that half cell reaction method, ion electron methods, oxidation number methods, anything, what do you do? That electrons count will not be affected. Electron count always depends only on the changes in oxidation states. So here what is the cell condition? That is ClO minus is converted into half Cl2. So what is the oxidation state here? The oxidation state of chlorine here is 0. Here the oxidation state of chlorine is -1. So how many electrons are involved for this reaction? It's only 1 electron. So what we are trying to do, let us take the first cell reaction. So it is half Cl2 is converted into Cl minus. So here also the changes is 1. So it is also 1 electron. So what are the potentials given at this condition? This is 0.54. This is given as 0.45. This is given as 1.07. And even he gave direct to this condition. So what we do is, suppose instead of taking all that, this is only just to inform or to know what is the cell reaction, how to write it at least. But do we require all this which we need to take? Let us see. So this is the actual reaction what we require. So how many electrons are involved for this reaction totally? Here the oxidation state was +5. Here the oxidation state is -1. So what is n factor here in this case? It's +5 to -1. The total change is 6. So it is 6 electrons. So +5 to 0, then into -1. So it is a total 6 electrons. But how I get this reaction? Maybe. Suppose I take this first equation, that is ClO3 minus plus 4 electrons with a potential of 0.54 is giving ClO minus. Let us say this is an equation 1. If I take this equation, that is ClO minus direct conversion into Cl minus, because the potential already given here. So how you get that potential also we can see from our application what we are doing now. So what is next? ClO minus plus how many electrons are involved during this now? This is +1 to -1, 2 electrons are involved. That is Cl minus. Let us take an equation. If I add these two equations, the Cl minus cancels. So I will get ClO3 minus plus 6 electrons, I will get Cl minus. So our required equation we obtain. So what is condition here is, when any half cell reactions are taken, if you want to predict the third half cell reaction potential, what we do is, we will convert the potentials into their Gibbs free energy changes, because Gibbs free energy changes are always extensive. You can add those potential, those free energies, but direct potential we can't add. So what we do is, what is suppose delta G for this reaction? We assume delta G for this reaction as delta G1. For this reaction as delta G2. What is for this reaction as delta G3? So since we are adding these two reactions to get this, what is delta G3 will be? Is nothing but delta G1 plus delta G2. So what is delta G3 or delta G? Delta G Gibbs free energy for a cells is nothing but minus of NFE. So what is this? Minus of number of electron for this third reaction, 6 into F into E naught of that what we require actually, or E naught of 3 you can write. What is this is minus 4 into F into E naught of that, because we are taking in this direction only. So 0.54 plus delta G2 minus of number of electrons here 2 F into E naught of that. E naught of this is given as 0.76 here. So it is nothing but 0.76. But you can cancel F. You can cancel minus. So what is E naught 3? Or what is the required potential for us? It's nothing but 4 into 0.54 plus 2 into 0.76 by total number of electrons 6. This 6 comes down. So it's only again calculation that we can do it and say what is the cell potential value. Clear? So which one we will get 0.8 or 0.7 or 0.6, that you can check. Clear? So how you got this is by adding these two. So what is the number of electron here, number of electron here, you add these two and divide, you will get this with 2. Because here 1 electron is involved, here 1 electron is involved. So total number of electron involved is 2 here. So it is overall what you get 0.76 is nothing but addition of these two. These two when you add it, you will get this, because half Cl2 cancels. So it is 1.07, 1 electron there, 1 electron here. So plus 1.45 by 2. So it is nothing but 1.07, this is 45, it's nothing but again 2, 5, 1. So somewhere same 0.76. That is how we got this 0.76. So you have to calculate now for this directly. That's it. So take the half cell reactions, whether you are adding it, whether you are subtracting it, that you have to see carefully. So directly we can say, if you are suppose adding the two half cell reactions, it is N1 E1 if you write in terms of normal simplest formulas and how to do it. So if you are adding the two half reactions, N1 E1 plus N2 E2 by the total number of electrons in the third equation, that is N3, is the cell potential for the required equation for which we wanted to calculate. So what is, if I suppose subtract the second one from the first one, then it is N1 E1 minus N2 E2 by N3, or reverse. If you are subtracting the first equation from the second one, then it is reverse, N2 E2 minus N1 E1 by N3, that's it. So here we are adding, so it is N1 E1 plus N2 E2 by N3, that's what we get, okay. Now, based on the given conditions here, or potential values, identify the correct statement here. So Mn plus 3 plus electron is converting into Mn plus 2 with a potential of 1.51 in acidic condition. Mn plus 4 is giving Mn plus 3, this one, potential. So Mn plus 3 undergoes disproportionation. Means Mn plus 3 may convert into reduced form and oxidized form. So what is mean by disproportionation here? Maybe Mn plus 3 should undergo reduction according to the given condition. To which state it has to go? Then we can only compare like this, because the potential values are given for plus 4 to plus 3, plus 3 to plus 2. So if you just write this in the scheme, that is plus 4 to plus 3 and plus 3 to plus 2. So what is potential values are given? Plus 4 to plus 3 is given as plus 0.95. Plus 3 to plus 2 is given as 1.51. And this is a simple condition you can remember. When the changes are same, suppose here plus 4 to plus 3, that is 1 unit. Then plus 3 to plus 2, then there is another 1 unit. So like already we discussed in the previous example. If the number of electrons and count is same like this. So n electrons here, n electrons here. If it is a situation, suppose 2 electron, 2 electron, 3 electron, 3 electron, 1 electron, 1 electron, then what is the simplest thing? This potential, suppose, is more than this potential. Then this species which is there in the middle will undergo disproportionation. Means if the successive reduction potential value is more than its previous reduction potential values, in such cases, always there is a disproportionation. So Mn plus 3 can undergo now disproportionation. It's what we do is, if I want to calculate, what I should do actually is, I should write this reaction, Mn plus 3 is converting into Mn plus 4 plus 1 electron. Then Mn plus 3 is converting into Mn plus 2 plus 1 electron. So this is the net equation that we get, 2. So 2 Mn plus 3 is giving Mn plus 2 plus Mn plus 4. So what is this one? This one is plus 3 to plus 4, means its negative value. So I take it as minus 0.95. 1 electron will be there. So 1 into that. So into this is again we can take it as plus 3 to plus 2, plus 3 to plus 2, 1.51. So plus 1.51. But we are saying how many electrons are involved in this reaction? Only 1 electron here also. So how many electrons are here? 1 electron here. Here also 1 electron. Here also 1 electron. Because the net reaction is supposed obtained. The total number of electron in any one of the reaction is nothing but the total So electrons in the reduction or electrons in the oxidation is the net reactions in the cell. So this is nothing but again 1. So like what we already said, we are adding or subtracting, we are adding now. So 1 into 951, 1 into 1.51 by 1. So total will be again positive. So when each cell is positive, then we say it is spontaneous. So I will get this is positive value because this is 1.51, this is 0.95. We get a positive value. So it indicates that the cell is spontaneous, means this reaction is possible. So disproportionation is possible. Done? Now, is there anything others? Maybe it's a spontaneous reaction. No, because already we are saying this is a spontaneous. So Mn plus 4 conversion into Mn plus 3, Mn plus 2 conversion into Mn plus 3. It's a reverse reaction for disproportionation. So this is not a possible. Then Mn plus 4 to plus 2 electron giving this. How to calculate this already we have seen. Add these two reactions and divide with 2. Then you will get not minus 1 point, anyhow both are positive. So we won't get this also. And Mn plus 4 is more stable than Mn plus 2. Mn plus 4 is more stable than Mn plus 2. Means when you are just seeing the potential, you are getting a positive value. Then the reaction goes in this direction actually. Because we are not getting this value negative. We will get this value as positive value only. Because it's both are positive here. So this value, when you see for this reaction, it's a positive. Means this reaction is spontaneous in this direction. Means Mn plus 2 is more stable than Mn plus 4. But not Mn plus 4 is more stable than Mn plus 2. So this is also not correct. Clear? Then. So only first option is correct for us. Next. In which of the following cells E cell is equal to E naught of the cell? So what is the simple condition already we have seen? If E cell has to be equal to E naught of the cell, Q value should be equal to 1. If Q is 1, then that log Q will become 0, then it becomes equal. So E cell becomes equal. So what is reaction quotient in the first case? So there is a careful condition to be seen. What is cell reaction in A? This copper oxidation will be there. Silver reduction. So Ag plus plus electron giving Ag. But when you want this net reaction, we have to multiply this with 2. So this is nothing but 2 gets cancelled. So Cu plus 2 Ag plus giving Cu plus 2 plus 2 Ag. So what is Q for this? It's nothing but copper ion concentration by Ag plus concentration whole square. So what is copper ion concentration given for us? 0.01. Ag plus concentration as 0.1. So that it becomes 1. So in this case it is E cell is equal to E naught of the cell. Next, platinum H2 giving pH is equal to 1. Then zinc. So what is this? pH 1. H plus concentration is 10 to the power of minus 1. And zinc ion concentration is 0.02. What is cell reaction in the B? So I write directly now what is the cell reaction? 2H plus. So we write H2 plus Zn plus 2 is giving 2H plus zinc. So what is reaction quotient is H plus concentration whole square by Zn plus 2 concentration. So which is nothing but here H plus concentration is 0.1 there. So 0.1 whole square by zinc concentration 0.01. So which is also 1. So this is also where E cell becomes E naught of the cell. Okay. So similarly in this, will it become equal now? No, because it is already 1. This is 1. So same condition at anode, but the different condition at cathode. So this cannot be the option. What is this is now again? The same condition like this, because instead of giving the pH as 1, he gave pH H plus concentration 0.1. So this condition is also where E cell becomes equal to E naught of the cell. Clear? So what is condition we should see is where the cell potential becomes equal to E naught of the cell becomes equal to E cell, where reaction quotient becomes equal to 1. So to increase the potential, Q value should be low. Now, a lead storage cell. So some questions can come in the lead storage batteries also. So lead storage battery, what happens is a normal rechargeable batteries that we will be seeing in two-wheeler or four-wheelers generally. So which is a lead storage battery, rechargeable batteries. We call it as cells, secondary cells, primary cells, like that. Clear? Where they can be reused. So primary cells we can't use again. Secondary cells they can be reused again. So the lead storage battery is a discharged, causes hydrogen H2SO4. H2SO4 is an electrolyte which will change in concentration from 40% by weight to 28% by weight. The final volume of the solution is, or original volume of the solution is, 1 liter. Identify the correct statements. So overall cell reaction is this. So direct theoretical part, directly what is cell reaction in a lead storage battery? This is a cell reaction. Lead rod, clear? Lead rod with lead dioxide coated is used as anode. That what we just take cathode, and lead rod kept in a lead sulfate is taken as anode. Lead dioxide coated is taken as cathode. So where lead plus 4 is converted into plus 2. Here lead is converted to lead plus 2. So this is oxidation. So this is anode. This is cathode. But during this H2SO4 also consumes. So the net cell reaction is this. This is okay. So how many moles of H2SO4 will be reacting? So effectively there will be 2 moles of H2SO4 reacts. That is also there. So that is also correct. Maybe in the given condition, what is the weight of H2SO4 if you just use it and calculate, let us see. Maybe. And the total charge that is released from anode cell to cathode cell is, how many Faradays of current is passed here? 2 Faradays. So what is 2 Faradays is? That is 2 into 96,500 coulombs. So what is this value is around? Now zeros, 10, so 3193. So it is 1.93 into 10 to the power of 5, which is also correct. Direct. So the mass of the electrolyte solution is decreased. So when you see the mass of the electrolyte, directly we can say electrolyte is already saying consumed. So the mass of the electrolyte is anyhow decreased. If you want to predict it, you can predict it. And so you can say directly 40% by weight, it is converted into 20% by weight. So the electrolyte is already consumed, he says. So anyhow electrolyte mass will decrease. That is also you can say directly. So the electrolyte mass decreases. Otherwise, if you want a calculation, means what is the amount of H2SO4 that might be consumed and everything if you want to take. Clear? Otherwise, there is no need of actually attempting this. There is no need of any calculation. Directly we can say. So 2 moles of H2SO4, 2 Faradays of current is passed. So 1.93 into 10 to the power of 5 coulombs. Everything direct. Clear? So all are correct. So coming to the next. E cell is given as 0.8 volts. So this is a cell. So we have a platinum rod kept in Fe+2 and Fe+3 solution. Then there is a permanganate ion in acidic condition in Mn+2 solution along with that, and there is a platinum rod. So when you have only solutions, means any metal surface is not there, we usually use platinum surface because it won't interfere with the cell reactions. So what is the condition to use as a platinum rod as a electrode? Is only where the platinum generally doesn't have any cell reactions, means any interference with the cell reactions. So directly the components which are in a different oxidation state they convert. So what is the cell reaction at this term? This is anode undergoes oxidation. So Fe plus 2 converts into Fe plus 3. If you use iron rod, then there is a condition that iron may convert as Fe plus 2. Iron metal may convert as Fe plus 2, or iron may convert as Fe plus 3, or Fe plus 2 may convert as Fe plus 3. So all these possible oxidations can be there at anode. So to avoid all that, to only say Fe plus 2 conversion only into Fe plus 3, we are using the platinum surface. So Fe plus 2 is converting into Fe plus 3 plus electron. What is at cathode will be? Its conversion of permanganate ion into Mn plus 2 in the acidified condition. So what is that? MnO4 minus converted into Mn plus 2. So we just add 5 electrons because the change in oxidation state is 5. This is the other way of balancing the reaction also. Then oxygens are now 4. So we add 4 H2O. So what is the charges? So only to balance the charges we will add H plus, that is 8H plus. So this is actually the cell reaction set individually at anode and cathode. So here to get the net cell reaction, because delta G naught values of components are given here. So we have to calculate delta G naught of MnO4 minus. So what we just usually say is, when you use the formations, we always say formation of products minus formation of reactants will be the delta G naught of the total reaction. But from the given value of potential, we can calculate what is delta G naught of the overall reaction. So what is actual overall reaction is now? It has to be now 5 electrons here, 1 electron here, it is multiplied with 5. So this 5 cancels. So this is 5 Fe plus 2 plus 8H plus MnO4 minus conversion into 5 Fe plus 3 plus Mn plus 2 plus 4H2. So what is delta G naught of this overall reaction is nothing but minus NF E naught of the cell or E naught of the reaction actually. So what is N for us? Total electron involved in this process is, whether it is a reduction, whether it is an oxidation. So I take 5, then Faraday 96,500 coulombs into volts, that is 0.8. So you will get this in terms of now joules. So if all values are there in kilojoules, you can convert this into kilojoules by converting into kilojoules by dividing with 1000, that is okay. But what is the G naught of the reaction? Overall G naught of the reaction is. So we just move into the next slide. Clear? So what is delta G naught of reaction will be? Delta G naught of reaction is delta G naught of products here, what is given there, minus whenever formations are there, whether it is a heat of formation, whether it is a Gibbs free energy formations, it's products minus reactants. So this is delta G naught of reactants. So what is delta G naught values that are given for the reactant and products? So what are the reactants here and products? Fe plus 3 for 1 mole, it is given, plus 3 1 mole is given. Let us see where it is now. Plus 3 1 mole is 10.2, but 5 moles are there here. Mn plus 2 is this, but 1 mole only. Water, it is again given here minus 230. So reactants, MnO4 minus we have to predict. H plus, directly you can take what is H plus given there, that is anyhow we will take delta G naught formation of the standard that H plus is 0 and delta G naught of Fe plus 2. So delta G naught of Fe plus 2 is minus 84. So all the values are given there. So directly we can use it and calculate from this. So this is if you convert this into kilojoules dividing with 1000. So what is this overall value you can use there and calculate it. Clear? So this is only calculation that we need to proceed. So from here we will just go to the next problem. So just substituting the products and reactants, otherwise we just write and we leave. So 2 into 96,500 into 0.8 by 1000, this is in kilojoules here. For the products, what are the products are? How many products? Like 5 Fe plus 3. What is Fe plus 3? 10.2 into 5. So what is that? 5 into 10.2 plus, sorry, what is next? Mn plus 2. Mn plus 2 is minus 229. This is per 1 mole. So this is also for 1 mole. So it is minus 229 plus, what is next? That is water. Water is 230 for 1 mole. For 4 moles, it's nothing but again 4 into minus of 230. This is overall of products. In the reactants, what are there in the reactants? That is Fe plus 2. What is Fe plus 2? Is minus 84. But you have again 5. So that is 5 into minus 82. No? 84. So that we will do. Next, H plus is anyhow 0. Mn plus 4 you have to calculate. MnO4 minus you have to calculate. So what is this is? This is nothing but 84 plus delta G naught of MnO4 minus, because it is also per 1 mole. So this is the only calculation that we need to proceed. Clear? Next. For the electrolytic production of NaClO4 from NaClO3 as per the equation, how many Faradays of current or electricity required to produce 0.5 moles of NaClO4, assuming there is a 60% efficiency. So again, only when there is an electrolytic cells or galvanic cell, what is the primary condition we are saying in electrochemistry is you have to predict only the basic cell reaction, what is the total electron involved. So what is cell reaction here already given, that is conversion of NaClO3 into NaClO4. So what is an oxidation state of, because others are like generally you just use for chlorine. So what is this is? Plus 5. It is changing into plus 7. So how many Faradays are involved here? So hydrogen is also converted from plus 1 to 0. So overall electrons involved in this process is nothing but 2. So what is mean by 2 electrons anyhow? It's nothing but 2 Faradays. So when you write any cell reactions there, then when you are getting the number of electron, the coefficient of the electron is nothing but your number of Faradays. So how many Faradays were involved here? 2 Faradays, that is for 1 mole. But how many moles of this we are taking? 0.5. We need 0.5. So we need to take 0.5. So for 1 mole we require 2. For half mole we require 1 Faraday. So for 0.5 moles we need 1 Faraday. But if the efficiency is 60%, what is mean by efficiency? 1 Faraday has to be utilized, but only that 1 Faraday should be equal to 60% of that what we pass. So how much of that we should take? Clear? So for 60% you need to take 1 Faraday. For that how much we should pass? So it is nothing but 100 by 60 Faradays. Because if you are saying 100% is utilized, 100% efficiency, 1 Faraday, you will be seeing 1 Faraday utilized. But if you pass 100 Faraday, only 60 Faradays are utilized. But if 1 Faraday has to be utilized, how much you should take? So it's nothing but 100 by 60 Faradays. So it's 10 by 6. Clear? So that is how much. Clear? So it's nothing but directly you can say this is 5, this is 3, 5 by 3 Faradays. Clear? So I think this, no, 1.67, 1.6 Faradays is okay. 6 we are getting. Coming to this, 2 later solutions or buffer solutions. One is 1m NaH2PO4 and 1m Na2HPO4 taken in 2 different compartments, 1 liter each. So 1 liter in one compartment, 1 liter in another compartment. So we have 2 compartments are taken. 1 liter is kept in this, 1 liter is kept in this. What are these buffers already is giving us? NaH2PO4 plus Na2HPO4. Same here, NaH2PO4 plus Na2HPO4. Then the platinum rods are kept here. So we kept platinum rods here. And we are passing current into this. But he is saying there is only electrolysis of water. Means there is a reduction of water, reduction of oxidation of water. Clear? That takes place. So where reduction takes place, where oxidation takes place? Reduction always takes place at cathode. Oxidation always takes place at anode. So if you are connecting this to the negative terminal, if you are connecting this to the positive terminal, assume that in this compartment, this is reduction. So here reduction takes place because it is a cathode. So in an electrolytic cell, negative potential means negative electrode is cathode. In electrolytic cells, positive electrode is anode. So this is cathode, this is anode. So here oxidation takes place. Done. So when we take reverse condition in the galvanic cell, anode is negative terminal there, cathode is positive terminal. So at anode always oxidation takes place there, cathode reduction takes place. So if you are taking this this is like a galvanic cell and connected, instead of connecting it to, let us say, an external source, this end will become generally anode, because in a galvanic cell always we represent the left side compartment always half cell as anode, right side always as cathode. So by default, with conventionally we say anode is on left side, cathode is on right side. So in a electrolytic cells, this anode becomes a cathode when it is connected to an external plate. So the cathode becomes anode. So when we pass current, what will happen? There is a reduction. So H plus reduction takes place here. So I can say water reduction, nothing but H plus reduction. Water oxidation, nothing but H plus is coming. So what happens here? Otherwise, you say water reduction gives, like, just use this basic condition. So H2O plus 2 electrons is giving H2 plus 2OH minus. So due to that, OH minus concentration will increase. That is what we are saying, H plus concentration decreases. So I can write instead of this, we say H plus concentration decrease. Oxidation will be reverse. So water oxidizes. So water oxidizes, what it will give? Then it will give O2 plus H plus 2 electrons. You write 4H plus, otherwise 2H plus 2 electrons, then it is half O2. So 2H. Okay, 2O2. Okay, done. Let us see this. Clear? So it is 4H plus will come. So here it is 4H plus and 4 electrons. Clear? So this is oxidation, this is reduction. So here also if you want to balance it, you can balance it. So this is 2H2O. So this is 2, this is 2, 2, that. So reduction of water is nothing but H plus. Similarly, you want to do this, you can say reverse actually. That is H2 is converted into H plus plus 2 electrons. So we usually say now, as what we see here, here there is a reduction. So H plus concentration decreases here. Here H plus concentration increases. So in this compartment, H plus concentration decreases. Here H plus concentration increases. Okay. So when we pass current, depending on the quantity of current what we passed, depending on the number of Faradays of current what we passed, here H plus concentration decreases, here the H plus concentration increases. So the buffer solution changes. So here what will happen? Here what will happen? That is the only condition. So what is the total current what we passed now? 1.25 ampere for 965 minutes. So let us see in the next, we will go. So what is total number of Faradays? So number of Faradays. So how we predict number of Faradays is quantity of charge in coulombs, that is current in amperes into time. So current in amperes was 1.25 and time was 965 minute. In terms of seconds, you should take minute conversion, that is by this, by total number of like Faraday, what is nothing but 96500. So this will cancel here. So this is 1.25 into 6. So 1.25 into 6, 3, 15, 12, 15, 1, 6, 7. Here, so it is nothing but 7, so 75 by 100. So 0.75, otherwise nothing but 3 by 4 Faradays. 3/4. So according to the condition H plus reduction, so what we see, for 1 Faraday we see 1 mole of H plus. So for 3/4 of the Faradays, we will see 0.75 moles of H plus decreases. So when H plus is decreasing, then what will happen? In a buffer, what is the general condition is? Suppose you take a buffer, normally Ha plus A minus is a buffer. There is a conjugate acid, there is a weak acid and its conjugate base that exists in a buffer. So when H plus concentration is suppose decreasing, what will happen? This concentration will increase, salt concentration will increase. So that meaning, let us say Ha is converted into H plus and A minus. So your overall concentration of A minus we take only as A minus concentration that is coming from the salt. So here if it is 1m, this is suppose 1m initially at T is equal to 0. When we pass current for some time, this will decrease, this will increase. So how much of this is decreasing? 1/4 of this is, 3/4 of this is decreasing according to the given condition there. So it remains 1/4. Here how much increases? This 3/4 increases. So the salt concentration increases by 3/4. Acid concentration decreases by 3/4. So what do we see? According to the given condition in this now, what is your acid is? This one will decrease by 1/4, 3/4. this one increases by 3/4. So in this compartment, what is its concentration is 1 by 4. This concentration is 1 plus 1 by 4, that is nothing but 5 by 4. Clear? In this, its concentration should increase, this concentration should decrease. Because H plus is coming, it will react with A minus and converts into HA. So there is a reverse reaction that takes place because the same current is passed into the both cells. So what you see is here it becomes 5 by 4, this becomes 1 by 4. So what is asked now? What is the pH in each compartment after the passage of that? So we know what is this type of buffer, acidic buffers. What is their pKa value is given. So directly we can use and calculate. So this is 7 by 4, no? This is not 5 by 4, 3/4. So we are adding 1/4. So it becomes now 7 by 4, this becomes 7 by 4. Okay? So what is pH formula for acidic buffers? pH is equal to pKa plus log of concentration of HPO4 2 minus by H2PO4 minus. So already you can use this, calculate pH in each compartment. So what is left side compartment? Here LHS, left side compartment. What is its pH is? pKa, what is given the pKa value? 2.15. But in the left side compartment, what is the concentration of acid is 1/4. Salt concentration is 7 by 4. So it is nothing but 2.15 plus log of 1 by 4 plus 7 by 4. RHS, right side compartment will be pH is equal to 2.15 plus log of 7 by 4 by 1 by 4. Reverse, that's it. Because here 3/4 will decrease, here 3/4 will increase. So this is the basic thing. A simple condition where in HA concentration decreases, A minus concentration increases. That is when H plus concentration is going down. So when this H plus is consumed, then the reaction starts moving in forward direction. That is how we directly use 3/4 is consumed, 1/3/4 is formed. Clear? Done. Okay. So let us move to the next thing. An object whose surface area is 80 centimeter square is to be plated with an even layer of gold with a thickness of 8 into 10 to the power of minus 4 centimeter. Then the density of the gold is 19.7 gram per cc. Then the object is placed in a solution of gold and with a current of 2.4 ampere is applied. The time required for the electroplating. So what is electroplating? Is coating a metal surface which is a reactive metal surface which is coated with a less reactive metal surfaces. So the electroplating is done by an electrolysis process. So assuming the layer of gold builds up evenly, means it's uniformly coated, happens uniformly. So the gold atomic weight is 197, but as you just use the condition here, Au plus 3 should undergo reduction to convert into gold to plate the surface. So how many Faradays are required? 3 Faradays are required for 1 mole of gold to coat. That means for 197 grams. So if 197 grams of gold has to be plated onto the surface of any plate, then how many Faradays we require? Because it is gold nitrate, it is Au plus 3, so it is 3 Faradays. So now what we need to require is density of the gold is given. So how much volume of the gold we coated it? So what is the volume of gold is? volume of gold what we quote it is nothing but the volume of the surface that we are doing it on the metal object surface what we are doing it. So that is the surface area into thickness, area into height. So that is 80 into centimeter square, 8 into 10 to the power of minus 4 centimeter. So this is total overall centimeter cube. So it's nothing but now 64 directly. So this is 64 into 10 to the power of minus 3 cc. But for 1 cc means what is gold density is given. So for 1 cc there will be 19.7 grams. So if I want to coat with this much volume, that is 64 into 10 to the power of minus 3, what should be the weight of gold? That is 19.7 into 64 into 10 to the power of minus 3 grams. So let us see what is the total Faraday required. So for 3 Faradays, 197. So for 19.7 into 64 into 10 to the power of minus 3 grams, how many Faradays are required? So what is total Faradays is? 3 into 96,500, we are doing in coulombs, into 19.7 into 64 minus 3 by 197. So this is 10 times. So this is 10 to the power of minus 4, but this is 10 to the power of minus 2 cancels, minus 2 will be left. So you can calculate what is the total Faraday, total number of coulombs. So this is totally in coulombs we are getting. Now what is current we passed? So this is the coulombs, charge current in coulombs. So current in coulombs is nothing but current in amperes into time. So 2.4 into time in seconds. So your 2.4 comes here. So this is the total number of or total amount of time for which we have to pass the current of 2.4 amperes into that cell to coat the gold on the metal surface uniformly. Clear? So this is what we do it. Done? Next. NO3 minus is converted into NO2 in the acidic medium with a E naught of 0.790 and NO3 minus NH3OH plus in acidic medium, and potential values are given. At what pH? Above the 2, above 2 will have same E value. Means you have to write the potential values, calculate the potential values at a particular pH. Now, assuming the concentration of others are except other species, this one except H plus is unity. Means whatever NO3 minus exists or NH3OH that exist or NO2 that exist, everything remains unity. Only H plus is. So what is this cell reaction actually? So NO3 minus into NO2. So what is condition is acidic condition. This is +5 oxidation state. This is +4. So we write 1 electron directly. So what is now charge like oxygen balance is H2O because 3 oxygens there. So then 2 hydrogens there, 2H plus. So that your charge is also balanced. 1 electron plus NO3 minus 2H plus. So total charge on LHS and RHS becomes 0. So this is the cell reaction there. So its E naught value is given already. So what is the cell reaction here? That is NO3 minus is converted into NH3OH plus. Whatever it is, nitrogen, what is the oxidation state? So if you just group it totally, that is NH4O plus. So how we predict the oxidation state of nitrogen here? Hydrogen should be +1, oxygen generally should be -2. What is this X? So what is this is X plus 4 minus 2 is equal to +1. So sum of oxidation states should be equal to total. So what is this is now X, this is +2, it comes here and becomes minus, so it becomes -1. So here it is -1, here it is +5. So +5 to -1, that will indicate that there are totally 6 electrons. But here there are 3 oxygens, 1 oxygen, we write H2O. So that is 2 times. So total hydrogens here 4 plus 4, 8. That will be 8H plus here. So these are the cell reactions. Individual cell reaction when we balance it. Done. Now what we need to predict here is, he said at what pH both the E value becomes the same. So what is E value for this we write? E cell value for this as E naught of this minus this as you use 0.06 by number of electrons there 1 log of everything whatever you write is unity anyhow. So NO3 minus or that you need not write. So it is directly 1 by H plus concentration whole square. But if you take this 2 here, it becomes plus because it is minus in the denominator. So otherwise you can take like this. E naught, this is suppose taken in the numerator, it becomes plus 0.06 log of H plus. But if you use minus symbol and take in this, so it is nothing but E naught minus 0.06 into 2. This is 0.12 I write directly. So this is 0.12. This minus if you take in this, it is nothing but pH. So for this, what is in this case? E cell in this case should be equal to E naught of that cell, that is E naught of the cell, let us say, minus 0.06 by number of electrons here will be 6 log of 1 by, in this case also again the concentrations are taken. He says there is all are remaining unity except H plus. So this is nothing but H plus to the power of 8 here. So if you simplify like that, what we get there is this 2 coming here is becoming like 2 times 0.12 pH only directly. So what I can write this one, this is E naught of cell minus 0.01 into 8 pH. So this is 0.08, this is E naught of the cell, this is E cell. But what he said, this is suppose cell potential values, these 2 values should be equal. So your this is E cell for this, it is E cell for this, both should be equal to 1 and 1. So what do you write? E naught values that RHS you should equate it to get the pH at which they become equal. It's again only just a substitution. Clear? So E naught of this you have to write, E naught of this you have to write here. So you have to predict where they become equal. Clear? Now, coming to the next. A sample of water from a large swimming pool has a resistance of 10,000 ohms at 25 degrees centigrade. When placed in a conductivity cell, it shows a resistance of that 10,000 volts. So from the let us say pool water we are keeping in a conductivity cell, it is showing that. When it is filled with 0.02 m KCl solution, the cell has a resistance of 100 at 25 degrees same temperature. Then 585 grams of NaCl is dissolved in the pool and stirred completely, and the cell solution is taken, a sample of that solution is taken and kept in the same conductivity cell. It is showing a resistance of again 8000. And given that, what is molar conductivity is of this. So this is like a conductance applications is. We always say the conductance and resistance applications as. Resistance is, I just go into the next page and do. Resistance of any electrolytic cell is directly proportional to length between the two electrodes and area of cross section between the solution. Means if it is a conductivity cell with a metal plates like this, the area that exists between these two solutions, these two metal plates, and this is the length. This is the area of cross section of the solution that exists totally, which is conducting, which is responsible for, which is actually favoring the conductance. So resistance of the solution, if the length between the electrodes increases, its resistance will increase. If area of cross section increases, then the total number of ions present in that solution will increase, therefore the conductance increases. So electrolytes are conducting due to the ions presence. So when the number of ions increases, conductivity will increase. So R is, you write as rho into L by A, where this L by A is nothing but what we call actually as cell constant. But what is conductance we say? It's nothing but 1 by resistance. So what is, you try to say conductance is equal to, this is 1 by rho into A by L. So nothing but this rho is, 1 by rho is nothing but a constant, is called kappa into A by L. So what is K, which is called conductivity, as conductance into cell constant. But this can be written as 1 by R also into cell constant. So we can just proceed that applications here with this. So what is we try to do is, first what was asked for us. What is cell constant of the cell, conductivity cell? So for that he gave KCl molar conductivity and he gave the resistance of KCl solution of a particular concentration. So from that what we can do, we can calculate this kappa. So what is the relation of kappa with molar conductivity? Molar conductivity lambda m is nothing but equal to specific conductivity into 10 to the power of 3 by molarity. So we have the molar conductance of KCl solution. So what is molar conductivity of KCl solution? 200. Molar conductivity of NaCl and molar conductivity of KCl. So what is this now? This is nothing but 200 into specific specific conductivity, conductance we say even, or conductivity kappa into 10 to the power of 3 by molarity of KCl is given as 0.02. So this is nothing but, K is nothing but equal to, now from here is 10 to the, what you get from here is, this 2 is nothing but 4, this 10 to the power of 4 into 10 to the power of minus 3. So only values I am just using. So the specific conductivity of KCl, if you write here, what is that is 4 into 10 to the power of minus 3, which we need to calculate. What is the resistance of KCl solution that is given here? Resistance of KCl solution is given as 100. So it is 100 into cell constant. So what we need is a cell constant. So it comes here, becomes 10 to the power of minus 1. So what is cell constant? So this cell constant remains for the particular cell, because even though you are filling with KCl, even though we are filling with NaCl, the cell constant remains same. Means in that conductivity cell we are filling. Means it is present only between this. Clear? So the cell constant value we already predicted now. So what we require here other than that cell constant here? So let us see what is there, else we need to calculate. So the cell constant is 0.4. What is conductivity of H2O? Means if the same conductivity cell you are filling, means the sample of some water is taken from the pool and kept in that conductivity cell. Its resistance was given as 1000. So what we need conductivity, Siemens per centimeter kappa. So what is this K value for this? It's nothing but resistance into cell constant. Cell constant is 4 into 10 to the power of minus 1, otherwise like what we said 0.4 sorry, by 1 by resistance, that is nothing but 10 to the power of 4. So it is nothing but 4 into 10 to the power of minus 5. So the next one, that is 4 into 10 to the power of minus. Then what is the volume of water that exists in the pool? So that we are actually predicting now through NaCl. So what is NaCl molar conductance? 125. So what is molar conductance of that 125 is equal to kappa of NaCl into 10 to the power of 3 by NaCl concentration. But we don't know what is NaCl concentration. So how much volume of water it is there in the pool? Some V liters it is there, but we dissolved totally 585 grams in it. So it is nothing but 585 by 58.5 into 1 by V. So this is nothing but 10 times 10 by V. So what is kappa will be? It's nothing but 125 into 10 by V by 10 to the power of minus 3, or 10 to the power of 1 by 10 to the power of 3. So overall this K. But what is this K? 1 by resistance of NaCl solution, that is 8000 into cell constant, that is 0.4. So from here you will get the volume. Clear? So but options are actually given wrong there, I think. So just because you are getting this as 2 times, so this is into 2 times you will get. So volume comes here. Here. So this is the volume totally what we are trying to predict. So just you can check that. So volume comes here, it becomes 2 times, so it will be 2500 somewhere, means it is 2 times of this. Okay? Done. So we are done with this. So there is different like electrolysis and galvanic cells and conductivity part we have taken. Okay? So we will see in the next session, we will meet in the next session.